So to start off Unit 2, we're going to talk about the history and the development of what we know about atomic structure. And I have a little timeline here to kind of give you some dates just for some reference for how long there is between some of these discoveries and actually kind of how long it's been since we've made another discovery about the atom and its structure. But I'm never going to ask you about these dates, but these are the people we're about to be talking about. And as we focus on each person, I'm going to have kind of 3 bullet points that you need to write down. And you can summarize the information that I'm giving you on that slide, but you need to make sure you're responsible for knowing what each person discovered, what kind of experiment they did, kind of how they did it a little bit, and then what they discovered about the atom and kind of how it's structured. And I might draw some pictures, or you can use your words to describe it, but you're responsible for understanding that new model of the atom and what it looks like. So our very first ideas about the atom actually came from ancient Greece, this guy called Democritus. And he actually was the guy that came up with the idea of an atom, except in ancient Greek it was called atomos. And that was just the idea that there is an indivisible, smallest unit of matter, now called the atom. So atomos actually means uncuttable, meaning that you cannot break it down past that point. Everyone else of the time thought that maybe if we had better technology, better cutting devices, you could keep cutting something down forever, just keep making it smaller and smaller. He never really did any true experiments. Remember, this is ancient Greece, but he based his ideas on kind of everyday observations, that everything was made of smaller and smaller parts. And so he figured that there would be a point where we just could not possibly cut something down any farther, that there was going to be a smallest uncuttable or unbreakable piece, and he called that atomos, the atom, basically. And so, like I said, you can kind of cut a piece of clay or a rock or a shell or a piece of cheese in half and in half again and in half again and just keep cutting it. But he thought and kind of figured there was a point where you would never be able to cut it. And that's what he called the atom. So he thought that atom, whatever that smallest bit of matter was a solid homogeneous sphere made of that original substance. So if you were cutting or breaking a shell down, then you'd end up with a teeny tiny little particle of a shell that was an atom of shell. And then there was a teeny tiny stone particle, the uncuttable teeny bit of stone that you could get down to was just a solid little sphere of stone or cheese. Whatever the substance was, he thought the atom was the same stuff. It was just smaller. Now, it might seem a little bit silly these days, but that's all that his technology could really discover. And so he started off our journey of the atom. And this was way, way long ago. It actually took a long time for anyone to develop anything more about what the atom is and how they work. So enter Mr. Dalton. And Dalton came up with some rules about atoms and how they act. And that's what we're going to be writing down here by these 1, 2, 3, 4, 5, the rules on how atoms act in general. And he derived these rules by studying how gases act and interact with each other. Now, Mr. Dalton didn't actually develop any new model of the atom. He didn't develop anything new from ancient Greek times. He's still assuming that atoms are solid, homogeneous spheres, just like Democritus did. But he did help us understand a little bit more about the atom, which led to some further discoveries. So his first rule about atoms was all matter is composed of atoms, small particles and pieces. And all atoms of the same element are exactly the same. Atoms can't be created or destroyed. They're indivisible, coming back to that idea of uncuttable or unbreakable atoms that Democritus came up with. That atoms combine in whole number ratios, kind of like H2O is H with 2 H's, 1 O, not H2.5 O 1.2. It's always going to be whole number ratios that they combine in. And in reactions, atoms only rearrange. They're not created or destroyed, coming back to that number 3. They just separate from each other and combine back in different places. And Mr. Dalton was actually pretty close to correct on 3 out of these 5 rules. So I do want you to write them all down, but you can put little checks by 1, 4, and 5 because those are still true. We still count on the fact that all matter is composed of atoms. They combine in whole number ratios, and they just get rearranged in reactions. But later in this video, on the next page, we're going to talk about some different examples of elements that aren't exactly the same as each other. And nuclear chemistry, now that we have that technology, can actually break down and destroy atoms, turn them matter into energy. So 3 out of 5 isn't bad. Now, later on, Mr. Joseph Thomson came up with the electron. So we were still thinking that atoms were solid, homogeneous spheres up until Thomson's time. And what he did, and that's what we have this little picture off to the side of, you don't have to draw this, is he shot cathode rays, which, if you know, it's kind of like an electron gun. They didn't know it was electrons at the time, but they just knew it was these beams of light. Cool, technology of the day. And so he shot these beams of light between magnets, and he noticed that this beam of light always bent towards the positive side. Even if he moved those magnets around, switched the positive and the negative, it always bent towards the positive. Turned them sideways, it always bent towards the positive. No matter where he put it, he saw the beam get attracted to the positive plate. So he realized, because opposites attract, they knew that much at that point, the beam must be made of something negative. And since the beam is coming out of, some gases and electricity, energy, that the atoms themselves must have some kind of negative piece to them. So that's how he discovered the electron. Now, technically, he called it something completely different, and the name's super weird, but that's what we know as the electron today. And so he incorporated these electrons into that kind of solid sphere. They call it the plum pudding model because he was over in England. Plum pudding's a thing over there. Over here in the US, I'd probably think of this as like the chocolate chip cookie model. That the whole atom is the cookie, with all of that dough being a positively charged, kind of mushy, well, he didn't think it was mushy, but a kind of dough surrounding these chocolate chips, which are the electrons. He just literally said, oh, there must be electrons in here, so he scattered them as little dots throughout the atom. We knew we had to have positive stuff canceling out the negative stuff because we'd never detected any charged stuff before, so it still had to cancel out. There had to be some positive stuff there to cancel out the negative stuff that he discovered, but he just kind of threw it all together. Called it the plum pudding model. Now, that is not what the atom really looks like, and Mr. Ernest Rutherford was a big part of developing our new kind of picture of the atom. What he discovered was the nucleus of the atom. If we were going to say he discovered an individual item, but really the concept or the idea that atoms are mostly empty space was his big discovery, that most of the area of the atom is empty and the mass is concentrated in a very, very small part in the center. And the way that he discovered that was by shooting some radiation at the most dense element known and easily kind of turned into foil. He took gold, rolled it into foil. So it was very, very dense, but very, very thin. And he surmised that this foil was probably very close together, single layer or two of gold atoms. So when he shot this radiation at it, if the atom was solid, like what we were thinking before, what Mr. Thomson had come up with, then these atoms in this radiation beam would bounce off of the solid atoms in the foil because they're very dense. They'd be like a wall that it bounces off on. But because most of the radiation went straight through, that meant that most of that atom was empty space. There was mostly nothing for it to be hitting. Even though there were atoms lined up there like a wall, they weren't a solid wall. It was like a chain link fence. So most of the beam went through. Now some of it did hit stuff and bounce off. So there was stuff there to hit, but it just wasn't most of the space that the stuff could hit. So that's how he came up with, okay, there's something hard enough to have that nucleus bounce off, or the radiation bounce off of something. So he called that the nucleus, and then most of the atom's empty space. So this is what we call the nucleus model. There's a very small, positively charged nucleus in the center with electrons scattered around, and these electrons are really, really small, not big enough to really deflect. You can't even see most of the dots that I'm putting down. They're just scattered around in these space. That's not really a dot that I was trying to put in there. So the atom being mostly empty space, including that edge. I put a dotted line around that edge there to show that there's not a hard shell, there's not a hard kind of edge to our atom. Most of the atom is in that nucleus. Then Niels Bohr came along, and he was the one that actually discovered that the electrons aren't just randomly scattered around in that empty space. He discovered that electrons actually orbit the nucleus in what we call energy levels. So they're kind of orbits. We actually call them orbitals, but we also call them energy levels. And Mr. Niels Bohr did one of my favorite experiments, and we're actually going to have a chance to recreate some of what he did with a little bit less calculations. He burned different elements into compounds and saw the light, the pretty colors that were produced from those elements and compounds. Now, he took very precise measurement of the energies of that light, and so he did a lot more work than just, pretty colors. But what he did when he was looking at those spectra, the different types of light that was produced, is he saw that only certain colors were produced. If you look at the kind of rainbow lights that I have up there, there's very specific beams and kind of lines in that spectrum where we see colors. And he looked at lots and lots and lots of elements, and he realized that even though, one element might have a different spectrum, a different set of lines than another, there were some certain characteristic lines he saw a lot of, but then there were some certain places he never saw lines. So because we knew that the light came from electrons, that was something that we discovered all the way back from Thomson and his experiments. So he knew the light comes from electrons. So if the light only has certain energies that are produced, that must be the electrons only have certain energy levels they can be at. So kind of fancy math going on there, but he developed what we call these days the planetary model, where we have electrons orbiting the nucleus in stable orbits, kind of like how planets orbit the sun. So a lot like Mr. Rutherford's model, except now instead of just a big empty space where the electrons are scattered, they're actually orbiting, moving in predictable orbits. Now, Mr. Heisenberg came along, and he completely disagreed with Bohr. And actually, a lot of other scientists were realizing that Bohr's experiment worked for some of the simpler elements, but it didn't actually work for more complicated elements, that their electrons weren't at as precise energy levels as we thought. So Mr. Heisenberg actually discovered that electron orbits are not predictable. He came up with what's known as the Heisenberg uncertainty principle. We'll talk more about that in just a moment. And Mr. Heisenberg, kind of like Mr. Bohr, used math to do most of his calculations. He didn't do fancy, electron guns and setting stuff on fire. He actually used matrices and invented new math to do quantum mechanics, but he basically managed to prove that you can never know a particle's exact position and momentum at the same time. And momentum is kind of like energy. Your physics teacher will tell you a lot more about that. But if we know kind of the energy level an electron's on, we can't actually know exactly where it is, which means that we can't have these nice, neat orbits where electrons are going round and round in little bitty circles, because then we would know its energy and its momentum, and he proved we can't. So we can't know its position and its momentum at the same time. It's just impossible. So what that meant for the atom, and you actually have this little diagram drawn there of the electron cloud model in your packet. He turned what were neat orbits into just some general cloud-like areas of probability where you are most likely to find an electron. But it's not just a ring, let alone an orbit, that it's going around in nice, neat little circles. And we're going to talk more about these shapes later, but they're not always necessarily spheres and nice rings either. Some of these look kind of weird shapes, which is where that word electron cloud comes from, because it's kind of poofy like a cloud. So these are only the most likely places where you're going to find an electron. I think they generally integrate to like 95% likelihood, but you never really know exactly where it's going to be at in these areas, just somewhere around in those areas. So the key thing to take away from this is that science is a process of learning, understanding, and discovering new ideas. All of these people were at the peak of technology for their day, but as technology developed, our understanding of the atom developed as well. So this electron cloud model is actually kind of old. It's almost 100 years old, and maybe in the next 5, 10, 100 years, we might actually develop a better model, understanding more and more about how the atoms put together. You, your kids, or grandkids might look back at some of these models, is even this Heisenberg uncertainty principle, and kind of scoff and say, "Oh, how silly they were." It's just a matter of technology and perspective.